Alright, hey everybody. So this video, like I promised last video, it took a little bit longer than I thought that it would. We're going to be talking a little bit about the development of vision, and we're also going to be talking about different parts of the brain and what happens whenever those parts cannot communicate with one another. So let's get into it. So if I were to ask you, do we learn language first or do we see things first? The answer seems pretty obvious, right? Oh, well, we can see things before we can speak. Obviously, right? Because you don't really speak until you're what? 1.5, 2 years old? You can see before then, right? But the question then is, how exactly do you know that? How do you know that you can see before that? Because I can't ask you as a baby if you can see, right? Because you're not able to tell me that you can see until you speak, which creates a problem with a lot of infant research, which creates a lot of problems with how we understand babies to perceive the world. So, for example, if I were to ask you, what is it that you see on the screen in front of you? You can tell me, and boom, there's the answer. You can tell me, right? Babies can't tell us stuff, so we have to be clever about the way that we test them. We have to try to find different ways of doing that. So, one of the things that this chapter is interested in is the development of vision, and specifically what parts of the visual field do babies perceive first. We haven't talked in this video series about spatial frequencies all that much yet, but that's really what we're looking at. What things in the visual field do babies perceive first? Low spatial frequencies or high spatial frequencies? And the way that we do that is not by asking babies questions, but by giving them what's called a forced choice procedure. Sometimes, people will get long-winded and they'll call it a forced choice preferential looking procedure or paradigm. And basically what they do, and this is really complicated, so feel free to write this down. They show a baby two images and they look to see what does the baby look at the most. That's it. That's all it is to it. So yeah, I'm joking. It's not that complicated. Basically, you're going to show babies two things. You're going to show them two books, and you're going to see whether or not they look at one book more versus the other. So you can do that. You can measure that, brain activation using EEG for that too, if you wanted to. But basically, we're going to be looking at what do babies look at more. So, and again, we haven't talked about spatial frequencies all that much, but we'll talk about them in a couple of videos. Children are not really good at seeing fine, small details that are handled by the parvocellular layers of the LGN. Instead, they're more adept at seeing big changes in their environment. So, children under the age of 4, not very good at reading. Part of that is because they just haven't gotten there cognitively yet, but it's also partly because before the age of 4, the eye hasn't finished developing. And because of that, we're not able to see lots of details. So, the center of our retina, the fovea, hasn't really finished forming yet. And because of that, that means that they're able to see big, broad shapes, but not really able to see fine details. So we know that because we can look at the anatomy and we can see how cones and rods develop as we get older and how those things don't really finish forming until we're 4 years of age. But we also know this by looking at behavioral data. So this is what I meant by the forced choice procedure, where basically you're going to have these two cards right here, and you're looking to see, which one of these does a baby look at longer. The idea being that the baby's going to look at the more interesting, more visually complicated of these first. So, for example, if a baby isn't able to detect the difference between this and this, that just tells us that they aren't able to quite perceive these lines yet. It won't be until later that they are able to perceive those. And so here in this particular case, and it's kind of creepy because it has somebody who's looking at the baby. This is all done with cameras these days, so you don't have a weird creepo peeking, But you're looking to see, of these two, which is the baby looking at longer. With the presumption being that the more visually sophisticated or more complicated, more interesting image is going to be the one that the baby is looking at longest. So you can do it that way. You can hook a baby up to an EEG, which is non-invasive. You just put those electrodes on their head, and then you measure what's going on here. There can be some early eye problems that are going to come up. We're going to talk more about those later in the semester, specifically when we talk about depth and perceiving things farther and closer to us. So when we start talking about strabismus and how our eyes can be misaligned, that is going to be something that we talk about then. I'll go ahead and get into that now because it's interesting. Sometimes whenever you're in kindergarten, you might remember one of your friends who wore an eye patch whenever they were growing up, and the reason for that is probably because they had two eyes that were not aligned correctly. And the way to remedy that is to put the eye patch over the strongest eye and let the weaker eye kind of gain its ability, gain its control, which is strabismus. If strabismus is not handled at an early enough age, it can lead to some mildly serious visual problems, because the visual system is really kind of, coming into its own in the first few years of life. So if you were to take a kid, and obviously nobody would ever do this, but if you were to restrict access to one eye, in other words, you were to put an eye patch over a kid's eye for no reason for the first 5 years of their lives, and they never got to see anything with that particular eye, what would happen is that eye would not really be able to detect a whole lot of details. It would not really be really able to detect line orientations or shapes or contours, because this is something that develops with age, not only anatomically but behaviorally. If we don't have access to these things, if we don't get to practice it, if we don't get to engage with it at an early age, we lose that ability. It's very much like when people talk about language and how, like, if you don't engage with language early enough, that by the time you're 10, 11, 12 years old, you can have some language deficits. The same is true here. Basically what happens is that the brain doesn't quite develop that part of your visual field correctly, and that can lead to some visual problems, which is part of the problem with whenever people have, let's say if they are unable to see from birth, why it can be particularly difficult to give something like a bionic eye to somebody who is in their 40s or in their 50s or in their 30s or 20s, that it would not be the same as if somebody had lost their sight after childhood, because the eye not only is the eye developing, but the part of our striate cortex that helps process that information is also developing as well. So here is a cool video that walks you through the flexibility of vision. In other words, they're going to take, in this case, a pair of glasses that turns your entire world upside down, and then see how quickly, if you can, adapt to seeing the world upside down. It's kind of a cool, fun video. Not going to be on the exam, just for your own amusement. Okay, so I've been promising split brain research. Let's talk a little bit about this. It doesn't really fit neatly into this chapter, but it is something that gets talked about a lot in psychology and in sensation and perception and in cognitive psychology. So when we talk about split brain research, you probably heard the oversimplification of the left brain versus the right brain. So we have the left brain, which is responsible for language and for logic and reasoning, and they have the right brain, which is responsible for creativity and art and things like that. And so, yeah, it's an oversimplification, but a lot of people like to think about the brain this way because I guess it's fun. It leads to these kind of cool advertisements like this, which are kind of cool, and it's really easy for somebody to say, "Oh, I'm left brain, and so I'm not very creative," or "Oh, I'm right brain, so I'm not good at math." The truth is, I hate to break it to you, that's a lot of nonsense. If somebody is bad at math, there's no differences in left brain activation versus right brain activation. That's not how brains work. So if somebody says like, "Oh, I'm not very creative, I'm left brain," they're just speaking colloquially. They're just speaking metaphorically. They don't actually mean the left hemisphere of their brain is more active than the right. Or at least hopefully they don't mean it that way, because that's not exactly how the brain works. But let's look at why this is a conception, why this is something that is perceived in our research. So this notion that certain hemispheres do different things is what's called hemispheric specificity. And I know that's a mouthful. Basically what it means is that the different hemispheres of our brains do different things. They handle their own types of information. They have their own jobs. They have their own roles. This is something that was very popular in the early 1900s, and then in late 1800s. It was discarded because it was a pseudoscience, because it was phrenology, if you remember that. And then was picked back up again in the 1960s. And the reason for that is basically by chance. That these neurosurgeons were coming across these patients who had some really, really bad problems with epilepsy. And so they suspected that one thing that they could do to help treat epilepsy would be to sever what's called the corpus callosum. The corpus callosum is going to be the neural fiber, the set of neurons that links your left hemisphere to your right hemisphere. So basically these people who had epilepsy, it was so bad that basically it was becoming a grand mal seizure. And so they wanted to limit that to just one hemisphere if they could. This is like a last resort, kind of surgery. And so they severed that neural fiber, and so if a seizure started in one hemisphere, it couldn't get over to the other hemisphere. Okay, great. And it looks like that actually worked. It did seem to have good benefits for people that had epilepsy. And I know what you're thinking, that sounds dangerous, right? But it turns out it didn't make as big an impact on their behavior as you might think. It didn't give them two separate personalities. It didn't give them, two perceptions of the world or anything like that. So at first it didn't seem like there was really any serious problems. It wasn't until several months and years later that people started noticing slight, strange oddities in the way that they perceived the world. So what happened is that after the surgery, these patients started having very specific cognitive problems. And when I say problems, I just mean difficulties under certain situations. So what they found is that whenever information was presented, let's say to one side of the visual field, it would change how you responded to that information. So here's an example. If something was presented in the left visual field, patients would not be able to say what they saw. So you're covering up one eye and you're seeing things in your left visual field. These people were not able to articulate what they saw, but they were able to draw it. They were able to correctly choose it with their left hand. And that's because their right hemisphere doesn't have a whole lot of access to language, but it can draw. It can pick things out. And remember, the right hemisphere handles the left side of your body, which is why your left hand would be able to choose this, but your right hand would not be able to. And I know, that's crazy, right? That's nuts to think about. That's really, really fascinating. But the opposite is also true, that if somebody was shown something in the right visual field, that these patients would be able to say, they would be able to articulate, yes, this is what I saw. I saw, a bumblebee or whatever. But if you got them to close their eyes and to draw using their left hand what it was that they saw, they would draw something completely different. They would not draw a bumblebee. They would draw something else. And that's because the left hemisphere handles language, the right hemisphere handles other things. So here is kind of what this will look like. So what we're doing is we're severing some of this stuff so that the left visual field is, we'll get over to the right hemisphere, but this hemisphere can no longer communicate with the left hemisphere. Here's another kind of diagram breaking it down. There's lots of cool videos to talk a little bit about this. After you separate these two hemispheres and they can't communicate, that they just kind of handle it in the best ways they know how. For the left for the left hemisphere, that's in language. For the right hemisphere, that is using patterns, drawing, arranging things that are not necessarily language based. So here's kind of an example where this particular person, if they have a word flashed briefly in the right visual field like this, it's going to go over to the left hemisphere. So this person would be able to say, oh, I saw a face. Okay. But if it was flashed in the left visual field like this, they would not be able to tell you what they saw because the left visual field didn't see anything. in the left hemisphere didn't see anything. But if, again, we were to show them on this side of their visual field, they would be able to draw it using their left hand. Why? Because here it is being processed in the right hemisphere, and the right hemisphere controls your left hand. So here's another example. Let's say that you're checking this out. You got your hand over your right eye, and so you see this particular thing right here flashing in that visual field. If this was a split brain procedure, you would not be able to tell me what it was you just saw. You wouldn't be able to tell me what it was for. You'd probably be able to tell me that maybe you saw something, but you wouldn't be able to articulate what it was, because the left hemisphere is all about language, and because this was in the left visual field, it goes over to the right hemisphere. So, would you be able to predict what you could do? You would be able to choose it with your hand. So if you were feeling back there and you felt a sandwich and you felt a screwdriver and you felt a cup of coffee, you would be able to correctly choose the sandwich as the thing that you saw. But you wouldn't be able to tell me what it was that you had saw. So you wouldn't be able to use language, but you'd be able to use other things with your left hand to be able to do that. So you'd be able to draw it, you'd be able to choose it. Another example. And this is where it gets even stranger. Let's say that you're focusing right here, and then I flash to you these two images, and then they go away. So, if I were to ask you, what did you see on the left-hand side of the screen? You would say, I don't know. But you would be able to say that you saw money in front of you, right? Because that was in one side of the screen. Okay, so if I were to ask you, I want you to pick two words that are related to what you saw. You would be able to select bank, but you'd also select chicken, even though that wasn't something that you said that you saw. And the reason for that is basically because the right hemisphere, that quote-unquote creative side, is going to create a story for us. It's going to create this narrative. And so it's going to give us a reason for why we chose that. So if you chose bank and chicken, and I said, why did you choose bank and chicken? You would say, well, because you can buy chicken with money that you have from the bank. Now remember, you wouldn't be able to tell me you saw a chicken, but those would be the two items that you chose here. And so basically really, really strange, right? We're not going to get into a whole lot of detail about these different kinds of phenomena this semester. We'll, sometimes in intro you talk about it, sometimes in cognitive psychology you talk about it, but it's just kind of one of those curious things that we know about the brain. And the reason why I'm bringing it up here is because this distinction of having the left hemisphere handle certain kinds of information and the right hemisphere handling other kinds of information is something that we're going to see again in the next chapter too, when we talk about perceiving different objects. But for now, we're going to talk a little bit more about spatial. Now that we talked a lot about the anatomy, let's talk a little bit more about how it is that we're able to perceive details. And I'm going to do that in a separate video coming up. See you later. Bye.